what IGNOU is doing in specific. May I request
we have with us Dr. M. Imran Khan, who is a well-known quality control man and expert in food analysis. He did his PhD from National Dairy Research Institute, Karnal, and has been associated with the food analytical labs like FRAC, Choksi and Arbro labs for last 5 to 6 years. Now he is with the food lab of Intertech India Private Limited. Dr. Khan, please.
The first methodology I will be speaking about the determination of volatile oil in spices. The basic principle behind this methodology is distilling the volatile oil over the boiling water bath, condensing, collecting the oil in a measured volume of xylene in a graduated tube. After cooling, direct reading of the oil volume separated from distillate. The methodology will be more clear if we will go by one by one procedure. But before going to the procedure, I will speak about the requirements of this method. So, volatile oil traps, it is a Clevenger type with joints, flask with magnetic stirrer, 1 liter capacity. It should have the round bottom and short neck with a standard joint and having except magnetic stirrer bar. The chemical required is only xylene. This should be a minimum of air grade. The procedure of this methodology is transfers the sample to 1 liter flask to yield 2 to 4 ml volatile oil. It means you should have the basic information about the product, so that you should sample accordingly. The resulting sample should give you at least 2 to 4 ml of volatile oil. Then add water to fill flask to half full. Insert string bar and place flask in heating mantle set over magnetic stirrer. Add anti-foaming agent. Clean trap and condenser with chromic acid solution before use and fill trap with water. Set the apparatus so that the condensate will not drop directly on surface of liquid in trap but will run down the slides. Start stirrer and heat mantle through variable transformer set at 90 volts or 63 ampere. If oil separates in graduated portion of trap or clinch to wall, add several drops of standard aqueous detergent solution through top of condenser. Repeat if necessary. The idea is to drop down all the oils into the contents. Distill the contents for 10 minutes after adding a detergent to wash it out of trap, and then add 1 ml xylene accurately measured to lighter than water trap. Distill until 2 consecutive readings taken at 1 hour interval, so no change in oil content. You need to distill until you feel that all the oil content extracted to the water trap. Then take 2 consecutive readings, and the readings should be same. There should not be any change in oil content. Then cool and read the volume of collected oil. Here you need to take a precaution. You should not read the oil content while it is hot. You should cool the content first. Then you will get the exact volume of the oil. If xylene added, subtract its volume and report oil as milliliter per 100 gram spice. The calculation part of this method is the volatile oil in percent volume by weight is A multiplied by 100 divided by B, where A is the volume of steam volatile oil in milliliter, B mass of the sample taken in gram. So, I have completed the first methodology. Let me speak about the second methodology. This is determination of starch in cereal grains by glucoamylase method. Starch is important because it converts into glucose The basic principle of this methodology is the test portion are hydrated and starch is gelatinized, followed by hydrolysis into glucose with glucoamylase at 55 degrees centigrade. Glucose is determined with glucose oxidase peroxidase reagent. The reagent required for this methodology is glucoamylase solution. This is 10 milligram or 30 IU per ml in water. The second reagent is D-glucose standard solution. To make a glucose standard solution, you need to dissolve 400 milligram anhydrous glucose in 1 liter of distilled water and let it stand for 4 hours to complete meter rotation before use. Third reagent is acetate buffer, 4 molar. The pH should be 4.8. Dilute 120 ml glacial acetic acid and 164 gram anhydrous sodium acetate to 1 liter with distilled water. The other reagent is tris phosphate buffer, pH 7. Dissolve 36.3 gram trihydroxy methyl aminomethane and 50 gram NaH2PO4 in 500 ml water. Adjust pH to 7 with H3PO4 at 37 degrees centigrade and dilute to 1 liter with water. Here the adjustment of pH is very important. The tris phosphate buffer should have the pH, it must have the pH of 7. So you need to take care at the time of analysis. You should adjust the pH at the time of analysis only. It should not be old solution. Then the other reagent required is enzyme buffer chromogen mixture. To make a mixture, you need to dissolve 30 gram glucose oxidase, 3 mg peroxidase and 10 mg O dianisodine 2-HCl in 100 ml tris phosphate buffer. The tris phosphate buffer is used to make the enzyme buffer chromogen mixture. Disperse O dianisodine 2-HCl completely in small amount of buffer before adding it to enzyme buffer mixture. Grind test sample to less than 0.5 mm size by passing through sieve. This is again very important. The sample should be ground properly. It should pass through the 0.5 mm size sieve. Sieve should be a technical grade sieve. Then determine moisture content of the sample. You need to determine the moisture content of the sample before going for a starch analysis. Weigh 0.5 gram sample in 250 ml dried and weight conical flask and add 25 ml water with string. While you are adding water, you should string the contents and adjust pH to 5.7. Here again the pH adjustment is very important. If the pH is not proper, you will not get the exact value of the starch. Boil gently for 3 minutes. After adding water and adjusting pH, you need to boil the sample for 3 minutes. Then autoclave for 1 hour at 121 degrees centigrade. Cool to 55 degrees centigrade. It means you need to autoclave the contents for 1 hour at 121 degrees centigrade. Then you need to cool the sample to 55 degrees centigrade. After cooling, add 2.5 ml acetate buffer and sufficient water. Sufficient water means the amount of water and sample should become 45 plus minus 1 gram. Immerse flask in water bath with shaker at 55 plus minus 1 degree centigrade and add 5 ml glucoamylase solution. Hydrolyze for 2 hours with continuous shaking. Filter into 250 ml volumetric flask and then wash quantitatively and dilute to volume. Transfer 1 ml aliquot containing 20 to 60 microgram D-glucose to test tube. Add 2 ml enzyme buffer chromogen mixture. After adding all these enzymes and other chemicals reagents, you need to shake the tubes and place in dark at 37 plus minus 1 degree centigrade for 30 minutes to develop the color. This 37 plus minus 1 degree centigrade temperature and 30 minute time is very important. You need to monitor this to very strictly and then immediately after 30 minutes of incubation time, you need to stop the reaction by adding 2 ml sulfuric acid 1:1, and then measure absorbance at 540 nanometer using a spectrophotometer, and prepare a standard curve from 0 to 60 microgram D-glucose per ml and a blank. After getting the absorbance, you need to calculate the starch percent by mass, and the formula is G multiplied by V1 multiplied by 100 multiplied by 0.9 divided by V2 multiplied by W, where G is glucose content calculated from a standard curve, 0.9 is conversion factor of glucose into a starch, B1 is sample aliquot in milliliter taken for color development, and V2 is the final volume in milliliter after hydrolysis of a starch, and W is the sample weight, that is in gram. Now come to the third methodology. This is determination of pH of food products by using pH meter. One of the smallest analytical procedure in any laboratory, but it is very important. Most of the time, if pH measurement is not proper, the other analysis will not give you the correct results. So this is one important analysis you must take care while working in the laboratory. The basic principle behind this is it is expressed as follows: pH is negative log of hydrogen ion, where hydrogen ion is the hydrogen ion concentration of solution in moles per liter. Measurement of electromotive force of a cell consisting of an indicator electrode immersed in test solution and a reference electrode. Contact between test solution and reference electrode is achieved by means of a liquid junction which forms part of the reference electrode. Requirements for a pH measurement is you should have the electrodes and potentiometric equipments, that is pH meter, calibrated against known buffer solution, a conical flask, and of course the buffer solution of known pH values, for example 4, 7 and 10. The procedure of the pH measurement is: place 10 gram of test sample in a dry conical flask and add 100 ml of cool recently boiled water. Agitate the flask until an even suspension free from lumps is obtained. Allow suspension to stand at 25 degrees centigrade for 30 minutes, agitating continuously or intermittently to keep the starch particles in suspension. Let it stand for 10 more minutes. Decant the suspension liquid into the electrode vessel and immediately determine the pH using a potentiometer and electrodes which have been calibrated against known buffer solution. One of the important factor is the temperature of test solution during the time of analysis should be reported along with the pH value. Now the fourth methodology is the determination of free fatty acids and acid value in oils and fats. The acid value is determined by directly titrating the material in an alcohol medium with aqueous sodium or potassium hydroxide. Acid value is the number of milligram of KOH required to neutralize the free fatty acid present in 1 gram of the oil or fat. Free fatty acids is calculated as either oleic, lauric, ricinoleic or palmitic acids. Some of the most common fatty acids in the food samples. The requirements of this methodology is the ethyl alcohol should be 95% volume by volume, neutral to phenolphthalein indicator. This ethyl alcohol should give a neutral result to phenolphthalein indicator. Phenolphthalein indicator solutions dissolve 1 gram of phenolphthalein in 100 ml ethyl alcohol, and standard aqueous potassium hydroxide solution should be 0.1 normal, or standard aqueous sodium hydroxide solution should be 0.5 normal. To obtain the result, you need to mix the oil or melted fat thoroughly before weighing. The mixing of sample either in the form of oil or in the form of fat should be mixed. Weigh cooled oil or fat in 200 ml conical flask. The weight of the oil or fat taken for the test and strength of the alkali used for the titration shall be such that the volume of alkali required for the titration does not exceed 10 ml. So you need to have a prior calculation, basic calculation, so that the volume should not exceed 10 ml. Add 50 to 100 ml freshly neutralized hot ethyl alcohol and about 1 ml of phenolphthalein indicator solution. Boil the mixture for about 5 minutes and titrate while as hot as possible with a standard aqueous alkali solution, shaking vigorously during titration. The calculation part of this methodology is the acid value is calculated as 56.1 multiplied by N multiplied by V and divided by W, where V is the volume of standard KOH or NOS solution in milliliter, N is the normality of standard KOH or NOS solution, and W is the sample weight, that is in gram. Now I will explain the methodology of determination of vitamin A content in ghee by HPLC. There are several methods refer the analysis of vitamins using HPLC. There are some methods in AOAC, AACC, American Association of Cereal Chemists. There are methods in other Indian standards. Most of these methods are same. Only the difference is it is based on the nature of the sample. If sample is containing more fat, you need to select a proper sampling procedure and sample preparation methodology. Today I will be explaining the determination of vitamin A content in ghee. Ghee is almost 99% fat. So here methodology is little bit different than the sample containing ghee, around 2 or 10%. If you will go through the proper literature, you will find the methodology in a different samples. The basic principle behind this method is the ghee sample saponified using ethanolic KOH and the unsaponifiable matter is extracted with diethyl ether. The vitamins comes into the unsaponifiable matter. Then vitamin A content is then quantified by using HPLC. The requirements for this method is the HPLC system, hot plate, micropipette, vortex shaker, weighing balance, water bath and rotary evaporator. The reagents required for the analysis of vitamin A is ethanol. The ethanol should be distilled, the potassium hydroxide of AR grade, the glycerol of AR grade, the diethyl ether of extra pure grade, and the standard vitamin A, and sodium sulfate anhydrous. The standard vitamin A can be in a acetate form or palmitate form based on your requirement. If the sample is supposed to have the vitamin A in acetate form, you need to take the standard of acetate form. But finally, you are saponifying the sample contents. So if the standard either in acetate form or palmitate form will become a vitamin A. For the determination of vitamin A, you need to weigh the 5 gram of sample into a dried iodine flask. The sample weight can be different depending upon the matrix of the analysis. If sample is containing sufficient amount of vitamin A, you can take the lesser amount of sample. If it is it's not having the sufficient, it's having a very low amount of vitamin A, you can have the more amount of sample weight. But if you are increasing or decreasing the sample weight, you will have to adjust the other reagents and chemicals accordingly. After weighing 5 gram of sample into a dried iodine flask, add 50 ml of 14% alcoholic KOH. KOH should be made in alcohol, preferably in methanol. Add 10 ml of glycerol into the flask. Glycerol acts as a antioxidant property. In place of glycerol, you can use the vitamin C, ascorbic acid, that is ascorbic acid, and as far as some other antioxidant you can also use. Place the flask on thermostatically controlled water bath at 65 to 70 degrees centigrade. Temperature should not be more than this or should not be less than this. If you are keeping temperature less than 65, then the saponification procedure may not be complete. if you are keeping temperature above the 70 degrees centigrade, then you may end up with the lower determination of vitamin A. After placing the flask on thermostatically controlled water bath, attach the condenser and reflux sample for 1 hour. Rinse condenser with 95% ethanol. Remove the flask from the reflux assembly. Close with a stopper and cool to room temperature. The attachment of condenser should be very proper. It should not leak from anywhere. Condenser should be rinsed with 95% ethanol, so that if there is any vitamin A droplets, any alcohol droplets containing the vitamin A on the wall of the condenser should go down to the contents. And after removing from the water bath, you need to cool the sample to room temperature immediately. Pour the content to a 250 ml separating funnel. Add 100 ml diethyl to it and stopper the funnel and shake vigorously for 45 seconds. Let the layer separate out and collect the aqueous layer into a beaker and ether layer into another separating funnel. You need to collect the aqueous layer in a separate beaker and ether layer in a another separating funnel. Pour again the aqueous layer into the separating funnel. Here this is the first separating funnel you have used to extract the vitamin A. So you pour again the aqueous layer into the separating funnel and extract with 50 ml ether. Repeat the extraction once again. You need to repeat this procedure once again. So there may be 3 or more than 3 extraction depending upon the vitamin A contents of the matrix. If you feel that 3 extraction is sufficient to extract out all the vitamin A from the matrix, then it's okay. Otherwise, you can go for another round of extraction. Combine all the ether extract into a separating funnel and then wash the extract ether with water till the aqueous layer becomes colorless with phenolphthalein. After combining all the 3 or 4 extracted ether to a separating funnel, you have to wash this with a 50 ml amount of water, volume of water for 3 times or maybe 4 times to make it colorless if you are checking with phenolphthalein. Filter ether into 250 ml flask. Throw sodium sulfate. While filtering ether into 250 ml flask, you need to pass this ether through a sodium sulfate layer, so that if there is any trace of water, it should remain with the sodium sulfate and the resulting filtrate of the ether should be water free. Then evaporate ether in a flask to dryness on rotary evaporator at 40 degrees centigrade. While drying the ether on a rotary evaporator, the temperature should not be more than 40 degrees centigrade. After drying then you need to dissolve the dried residue in mobile phase. I will let you know the composition of mobile phase in a subsequent slides. While dissolving the dried residue in a mobile phase, you need to take care of the volume of the final extracts, so that the same volume can be considered while calculating the results. Treat standard vitamin A either in the form of acetate or palmitate as described to test sample while using 2.5 mg of standard. Standard vitamin A should also be proceeded for same as you have done the vitamin A analysis of a sample. Only thing here, you need to take only 2.5 milligram of weight. SPLC instrument condition. The column required is ODS, octadecylsilane, C18. The column temperature should be ambient. The composition of mobile phase is acetonitrile, methanol, dichloromethane, and the ratio of 7:0.5:3. The detector requires UV visible and wavelength is 310 nanometer and the injection volume is 20 microliter. After making all these conditions, you need to run the mobile phase for half an hour time, so that the instrument gets conditioned, the column should be conditioned. Then you inject one set of standard and then one set of blank using the mobile phase, so that if there is any trace of standard you have injected prior to the blank should come into the blank, and then you should inject this sample using this same instrument condition. After getting the peaks and peak area of the sample as well as standard, you need to calculate the vitamin A content of the particular food product. For that, you need to have the peak area of sample divided by peak area of standard multiplied by standard concentration, that is divided by sample weight multiplied by injection volume of sample and divided by injection volume of standard, then multiplied by the purity of standard you have used, and again the potency of the standard you have used. So, I have completed the chemical analysis of food and quality assurance part today.
Dr. Imran, may I request you to, because some of the students are maybe our fresh graduates, if you can tell something about basic about HPLC, that high pressure liquid chromatography, like special features or what precautions they should use in the operation of HPLC.
HPLC is a high performance liquid chromatography. Initially it was termed as high pressure liquid chromatography. Then later on, because of its very good performance, it was retermed as high performance liquid chromatography. The best I can explain how it works. It is having some basic components like mobile phase. Mobile phase is a liquid form because it's a liquid chromatography, and the composition of mobile phase depends upon the analyte, target analyte you are doing in a particular matrix of food. Then there is a stationary phase. Stationary phase is nothing but is a column, and the column chemistry also depends upon the matrix or analytes you are targeting. The most of the cases of food analysis, the C18 ODS column is required. C18 is the carbon chain 18 coated on a silica base and cased in a stainless steel column. Then the other part is the injection module. The injection module can be a manual one, it can be an auto sampler. You can fix the number of standards, number of samples in an auto sampler and program it through a computer. The instrument can inject all these programmed sample or standard one by one in a same sequence whatever you have given in the program, and otherwise you can inject manually through a manual injection module. Injection volume depends upon the concentration of particular analytes in the sample. Suppose if it is the sample is having very concentrated amount of a particular analytes, you need to inject a very small amount of a small volume of the sample, maybe 1 microliter or 0.5 microliter. If sample is having less quantity of vitamin A or any other analytes, you need to inject little higher volume. It can be, in general it can be 20 microliter. In some cases, like where the analytes is in a very trace amount, there you need to inject very high volume of injection volume, that is maybe 400 or 500 microliter. This is in the case of, like, if you are doing something in a test analysis like pesticide residues or antibiotic residues or any other residues where the volume is required towards the higher side. Then there is a pump. The pump is required to carry out the mobile phase from the mobile phase storage to the column. While going to the column, it takes the sample or a standard injected through the injection module, the sample and injection along sample or standard along with the mobile phase goes to the column, and it gets separated over there. Then the same while separating in the column, the similar compounds or similar analytes get separated altogether, get attached to the column and released from the one part of the column, then again attached to the another part of the column, and then again released from the column, and comes out of the column. While coming out of the column, the same analytes comes together, and the other property characteristics of analytes comes later. Like that, the separation takes place in the column, and the analytes which is coming out of the column first, it goes to the detector first, so it gets detected there, and then the second bunch of analytes comes out from the column, it goes to the detector, and then it gets detected there. While coming to the detector, the detector will detect the analytes in the same order, which is coming first and which is coming later. So based on the detection in the detector, it gets detected and it gets the retention time of a particular analytes. Retention time is nothing; it is the time travelled by an analyte from the column to the detector. Then, of course, I have spoken about the detector. The most important part of the SPLC is detector. Today we have spoken about the UV detector. There are some other detectors like RI, refractive index detector, fluorescence detector. Depending upon the use of analytes, characteristics of the analytes, we use the detectors. For most of the vitamins analysis, we need UV detector, except vitamin E, where the most recommended detector is fluorescence. For sugar analysis, we need RI detector, that is refractive index detector. It works on the principle of refractive index only, and the fluorescence index can be used for aflatoxin analysis, amino acid analysis. Then the UV detector can also be used other than the vitamins for antioxidant analysis. But altogether, the heart of an SPLC system is a column, where most of the separation takes place. Basically, whatever analytes present in the food matrix comes to the column, it gets attached to the carbon chain present on the silica base. Then, because of polarity of different analytes, it gets attached and detached process, and then it comes out from the column and goes to the detector.
What are the precautions which any chemist should take into account?
The first and foremost precautions needed to be taken care while using HPLC system is the sample preparation. And in the sample preparation, the filtration of this finally the filtration of the sample is very important. If there is any trace of residue other than the analytes and solvents, it gets remains in the column, and it chokes the column. It will not allowed to pass other liquids or other analytes through the column. So you need to take care of the sample preparation, and the foremost, as I said, it is a filtration. You should filter the final volume of the sample either with 0.45 micron filter paper, and it's better to have a 0.2 micron filter paper in place. And there are other precautions like whatever reagents or chemicals you are using, it should be extra pure grade or at least a minimum of AR grade. So these are precautions one need to take care while using the SPLC system.
Thank you, Dr. Imran.